In this problem, we have a satellite that's in a circular orbit around the Earth. And the satellite is at an altitude of 20,372 kilometers above the Earth, and it's actually the surface of the Earth, which is very important, and I'll get to that later. And we need to find the orbital period in sidereal days of the satellite, which just means that we're going to have to convert our final answer. Well, I'll start by drawing a picture. This will be the Earth. I'll call this E. And this will be the satellite that goes around the Earth. So this satellite is at a height from the surface of the Earth, and this is 20,372 kilometers. So I'll just call this D1, and this will be 20,372 kilometers. So this will be D1. But when we do our equation for the force of gravity, we also have to account for the radius of the Earth, which I'll call D2. And D2, which is the radius of the Earth, is 6,371 kilometers. So this entire distance here, which I'll just call R, will be D1 plus D2, and R is going to be equal to 26,743 kilometers. I want to convert this to meters right away because I'm going to plug this into an equation that has a G in it, and G is in meters, so it has to agree in its units. So R will be 2.6743 times 10 to the 7 meters. Now I'm ultimately solving for orbital period, which is t. This will be equal to 2 pi r over the orbital velocity. Well, to get the orbital velocity, I'll start with F equals ma. Since this is uniform circular motion, a is going to be equal to v squared over r. So F will be equal to mv squared over r. And this is the force of gravity, so it'll be g times the mass of the Earth times the mass of the satellite over, this will be r squared. This will be equal to the mass of the satellite, the orbital velocity squared, over the radius. The radius is going to cancel. We'll be left with 1 on the left side. And the mass of the satellite will also cancel. We'll get that v squared is equal to g times the mass of the Earth over the distance from the Earth and the satellite. Take the square root of both sides, and we'll get that v is equal to the square root of g times the mass of the Earth over r. Now I can plug this velocity into here, and I'll get that the period is equal to 2 pi r over, it'll be the square root, gme over r. So the period will be equal to 2 pi r root r over root g mass of the Earth. I'm going to make myself some room to plug in the numbers. I'll write this a little bigger. Period will be equal to 2 pi r root r over root g times the mass of the Earth. So the period will be equal to 2 pi. And again, this r will be the total distance from the center of the Earth to the satellite, which will be this number here. So this will be 2.6743 times 10 to the 7 meters. Now, since it's r root r, you can combine these and have uh, r to the power of 3 halves. This will be over the square root of g, which is 6.67 times 10 to the negative 11. And it'll be times the mass of the Earth, which is given as 5.972 times 10 to the 24 kilograms. And we'll get that the period is equal to 4.355 times 10 to the 4 seconds. Now, since we need to convert this into sidereal days, where one sidereal day is 86,164 seconds, I can then divide this by 86,164 seconds. And I'll get the period is equal to about 0.505 sidereal days. And that is your final answer. Thank you for watching.